So just moving on, what we've done here is we've just written down the values that we had before. So you can see here, we should show we've got a total current, and we've got our voltage drop across R1, and we've got the voltage drop across the parallel right combination. And we're also written down the current flowing through R2 and the current flowing through R3 of the parallel combination. Now the first thing we've calculated here is what is the total power of the circuit. So your total power is your supply voltage times your total current. So we've got a 9 volt supply. We know we're drawing 2.42 milliamps of current. So the power usage of the circuit is 21.78 milliwatts of power. We've done the same thing for this combination over here. As you can see here, we've just written down all the values that we calculated before. And you can see here for this circuit, this is operating on 12 volts. So again, your total power is your supply voltage times your total current, which we've got written up there, and we end up with 84 points. So working on this circuit here, with the 9 volt supply, what we've done now is just worked out what the power consumption of each of the resistors is and see if it compares to our total power consumption for the actual circuit. So working on the parallel circuit here, we've got the power at R2, so the power consumption of this resistor, which will be your voltage for your parallel times the current passing through IR2, and we've got 5.37 volts, that's the voltage from there to there, measuring across here, and we have a current of 1.63 milliamps that we calculated before for IR2. And you can see here that we've got a power consumption of 8.75 milliwatts of power for here, and doing the same for R3, we end up with 4.24 milliwatts of power being consumed by R3. Now we have to take in R1 as well, and R1, and this is where you've got to be careful what voltages you're using here. R1 is the voltage drop across R1, so that's 3.63 volts as you can see there, and the total current, because you've got the total current passing through R1, and the total current is 2.42 milliamps, and we end up with a power consumption of 8.78 milliwatts of power for that resistor. If we add all these up, you'll find that they'll be close to 21.78 milliwatts, which is the total power of the circuit being consumed. So we've done the same thing for this circuit here, containing 3 parallel resistors and a series resistor. The power consumption of R1 worked out to be 74.76 milliwatts for the parallel sections, and keeping in mind that you must use the voltage drop across that parallel section, which we worked out is 1.41 volts. So 1.41 times the current through R2 end up 602.5 microwatts. R3 is 1.41 again times the current through R3, which is 9.04 milliwatts, and the power consumption of R4 again, which is 1.41 times the current through R4, ends up being 292.4 microwatts. And if you add those up, you'll find that they'll come, these 4 power values here, it should come very close to 84.72 milliwatts of power. There are rounding errors in here, as you can imagine, with reference to just rounding to 1 or 2 decimal places. It gives us all the information that we need to know, especially with the right selection of the resistor values that we may have to use, whether they're quarter watt, half watt, or whatever. And the same for this circuit here. We also know what our total power consumption is, and from that you could basically work out, you know, like how long that you know, a 9-volt battery would supply, you know, supply that power for, or a 12-volt battery would supply that power for, etc. So some basic calculations, but it gives us all the information that we need to know, and from that this can be applied to many other circuit configurations within electronics.